so today what we want to talk about is different functions. So here's just a real quick recap of all the things that we know how to do. So we know the constant rule, right? We know if we have 5 cosine of x, right? If we have to take the derivative of that. Well, let me make it even simpler. We'll make it sine of x so that we know the sign change. If we have 5 sine of x, what can y prime be in that case? I shouldn't put an equals. What can y prime be in that case? It's the derivative of 5 sine of x.
5 cosine.
Perfect, yes, exactly. Constant rule just says separate it, leave the 5 alone, and then take the derivative of that. And this seems really useless in this case, but in a lot of cases it's pretty helpful, like 12 over 3x squared, right? Well, we could actually call that 12 over 3x to the negative 2, and then just leave this alone, 12 over 3, which is actually 4, and then do negative 2x to the negative 3. You see what I'm saying? So constant rule is helpful. Not like as helpful as you might think, but it's helpful. Power rule is what we just did there. Take down the power, subtract 1 from it. Constant multiple rule means like if you have some, actually this is the constant multiple rule, if you have something multiplied by it. So actually, my bad, constant rule means that the derivative is equal to 0 of any constant, right? Constant multiple rule is what I was actually showing up here. So this right here was actually constant multiple rule. Sums and differences, you can just take the difference of, you can take the derivative of each thing separately, each chunk, each term, right? So we kind of know that. And now our favorite, products and quotients, which is all of that big formula type of stuff. So do you feel comfortable? We kind of know this all, more or less? We've learned it? Okay. But we still can't take the derivative of that. And the question becomes why? What is special about this that we can't take the derivative of it? Anybody know? Like, does anybody know what it is about this? Like, I could tell you why we can't take the derivative of it. Yes?
It's 2 terms.
Yeah, it's 2 terms inside of a square root. So it's actually because it's like embedded. It's like an onion, okay? So anything that's like an onion, we can't take the derivative of. I could tell you y is equal to cosine of x, and you could tell me the derivative, y prime is equal to what? Negative sine of x. Okay, perfect. And you have no issue with that. But what if I told you y is equal to sine of 2x? Now what do you do? Well, you'd like to say it's cosine of 2x, right? But we haven't technically said that, and it's actually not. There's actually a little bit more to it. So this is kind of where we're going with this. I'll erase this. We can always fast forward back to that. Pretty cool. So here's the deal. We need to break it down into an inner and an outer. Okay? So what could you take the derivative of? You could take the derivative of, we would be okay if it was like, I don't know, let's say it was like s equals the square root of t, right? Well, what would s prime be? How would you do that? Yeah, Abby? Yeah, you can make, well, I would make this t to the 1/2 and then derive that, right? So then what do we want to do from there? Yes?
1/2 t minus t to the, no, 1/2 t to the negative 1.
Good. So we can do it. We can actually take the derivative of this as well, but we don't really know what to do about that inside thing. So that's our problem. So I think, actually what I did here was, yes, the hand, okay. So we're going to use this over there. It's kind of funny, but it works pretty well for understanding this. I haven't taught it this way, but I've done this with a lot of different classes, and it works pretty well. So this right here is the hand that's going to cover up that. So we have the square root of hand. So if this is the deal, if it's the square root of hand, what do you think y prime is? You can use hand in your answer. Yes?
1/2 hand to the negative 1/2.
Very good. Yes. It would be 1/2 hand to the negative 1/2 power. So we could actually do that. That would be okay. The thing is that whenever we have this situation, we actually have to take the derivative of hand at the end. So we have to multiply by the derivative of hand at the end. That's what's happening. That's what's different about this. Okay? So take the derivative of the inside and multiply it by it. There are a bunch of reasons why this is, but none of them are really super intuitive. So we kind of have to memorize it and just do it. We kind of just have to go in faith. So I guess the question becomes, with this example, if we don't really want this in terms of hand, how do you think we would find the real derivative here? What do you think dy dx would really be? Thoughts? Yes, Abby? So start us off. Let's get this form at least first, right? So we're going to do, we're going to take 1/2 down, right? Isn't this equal to 2x plus 1 to the 1/2? So how do I do the derivative of that? Just tell me how you think it would be.
1/2
Yep.
times 2x plus 1 all over.
Yep, you don't have to simplify yet. It's okay. It's the negative 1/2. Okay, that's fine. No problem with that. So, okay, so we're going to start with 1/2 2x plus 1 to the negative 1/2, okay? And here's the chain rule. This is the chain rule. I'm about to do it. You need to look at the inside. Normally the inside's x. Until today, it's always just straight up x, nothing else. But today it's not, and you have to take the derivative of that and multiply by it. So what is the derivative of the green? Just the green. What's the derivative of just the green? 2. That's it. Yeah. That's it. That's the chain rule. That is the chain rule. The chain rule is a very important rule. I can't stress this enough. Huge, very important rule, okay? I tell a story of one student who took the Chapter 2 test and forgot the chain rule, and it was not pretty. You know, you just forgot it on everything. So the chain rule is a big deal. It's very important. Now we can simplify. So I'm hoping that this is kind of intuitive for you. This is no big deal. We cancel those out, so we have 1 over the square root of 2x plus 1. That's our actual answer. We move that negative exponent to the bottom. Okay? But don't try to simplify in the same step. Make sure you give yourself some time. Questions on that so far? Shall we do some more examples? Yes, Annette.
So it's just, you take the middle part, you find the derivative of...
You multiply by the derivative of the inside. Yep. That's all you do, really. And you do it the normal way you would think of doing it. And the hand might help a little bit, right? So we'll just kind of try that. So let's see, did I have any other notations? Oh, so sometimes you can think of it as being broken up. So when you have some different things, f of x, right? This is the outer. So if you look at the outer function here is the square root function, right? The outer function in this example, right here, I'll pull this down. Darn. Square root of 2x plus 1, right? So the outer function, right, is the square root function. That's what's on the outside. And what's on the inside? Well, the inner is this, so that's the g of x. So this is how they're going to write the notation for it. You guys are familiar with this, right? F of g of x, a composition of functions. So when you have an onion, like a function in a function. So let me show you how they would do this. All right, so the chain rule, the best way to say this is if y equals f of u, then y prime equals f prime of u times u prime. Okay?
That wasn't too bad.
Yeah. Okay, well, great. So this is the easier way of looking at it. U is whatever's on the inside. U is hand, if you'd like to think of it that way. I'm putting my hand in front of the board, right? You just take the derivative of whatever you see on the outside, and then you multiply by the derivative of the inside. Here's the more complicated way of looking at it. You don't have to write this down because it's just a more complicated notation. This is a professional way of saying it. This is definitely more professional than the thing above, but both achieve the same goal. This is saying, here's a good notation, the derivative of the composition of functions is going to be the derivative of the outside function, right? Here's the prime, with the inside left alone, times the derivative of the inside function. That's what they did. Not a better way of looking at it, I don't think. More complicated, but also more professional. My way is a little bit more like kindergarten, I guess you could say, type of way of writing it. For calculus, when it comes to calculus. All right, so let's do an example. Here's a trig example, okay? So let's try this one. It's the equation of the tangent line when x is equal to pi over 4. So I'm throwing in the equation of a tangent line just to be, extra annoying, because I know that that's going to keep coming up. But let's really focus on the chain rule more than anything. So if this is the case, if this was the case, does anybody want to tell me what they think y prime would be? If cosine of hand, you can use hand in your answer, so it's okay. What would it be? Derivative of cosine? Yes.
Negative sine of hand.
Very good. Negative sine of hand. So we would take that and we would copy it there. And we would not be done because we also have to include multiplying by the derivative of that inner part. So multiply by the derivative of the inner part. Well, here's the thing. I'm really just covering it up to make your life better. But in reality, it's 2x. So what goes inside the sign? 2x, yes? So I took the derivative of cosine and I made the derivative of cosine sine. So the derivative of cosine is sine. And now I did nothing to the inside. But now what is the last step of the chain rule, the most important part? Multiply by the derivative of the inside, which is simply 2. And so you have negative 2 sine of 2x as your final answer for y prime. Now, y prime is aka what? There's a lot of things we can call y prime. We can call y prime what? What are some terms you would like to use for y prime? There's a lot of right answers. dy dx, the derivative. What else is it?
Slope of the tangent.
Good. That's really relevant, right? Because as you can see, Stacia says slope of the tangent line, and we're looking for the equation of the tangent line. So we now actually have the slope. We have the tangent line is going to be whatever, and it's going to have the x values and the y values. But right here is going to be the slope of it, whatever it is. So do we have any x values or y values we can plug in now? Yes. We have the x value. That's helpful. So we have the x value, which is pi over 4. We put that in. Do we have a y value that goes to that pi over 4? How would we get a y value that goes to that pi over 4? And that's a normal y value. A normal, regular, everyday y value. How would we get it? Yes?
Plug it into the equation.
Plug it into the equation. Which equation?
The second. The first one.
Top one, yes, exactly. That's where people start to go, that's where they go downhill, They plug it into the derivative, but we don't really want that. That's how we get slope. So here we plug in the pi over 4, which is times 2, so we need cosine of pi over 2. And cosine of pi over 2 we hopefully already know to be 0. And pi over 2? 0. So we have 0 here. So that's our point. We still need a slope. What is going to tell us our slope? Let's try to get those all together now. So I'm going to circle slope. What else represents slope? Where are we finding our slope here in this maze, this labyrinth? Is the original equation the slope giver? No. Okay. All right. Well, what are we left with? Yes, this right here is how we're going to get our slope. So we want our slope at what time? I know it's not time, but at what place do we want our slope? Yeah, pi over 4. We can only put in an x right here of pi over 4. So really our slope, if you like, is equal to negative 2 sine of pi over 2, because I took pi over 4 and I doubled it. Sine of pi over 2, I think that's 1. So our slope is actually negative 2, and that's what I'm going to put here, negative 2, and I'm done at that point. Okay. Now a lot of this wasn't, and I'm sorry I get so cluttered so fast, a lot of this wasn't the chain rule. The only thing here on this whole page that was really the chain rule, the only time we actually used the chain rule in all of this mess was right here. When we took the derivative of this, we left it alone. And then we very, very, very clearly took the derivative of the inside right here, this part. This is getting to be a disaster. That's sad. we very clearly took the derivative of this part and made it 2. That's really the chain rule. The yellow highlighting is the chain rule. So let's keep moving. Let's see how long our video is now. 15. Okay, I want to stop it pretty soon. Let's see if we can get one more example in. Why don't you try this one? Y equals something squared. I'll show you what it is. This. So why don't you just try to find what dy dx is? Dy dx. Okay. If you want to pause, I'm going to put the answer up on the video, so you want to pause right now.